Okay, welcome back, everybody. So far we have finished looking at what goal one was. Yeah, so we replaced the word quiver by a finite dimensional associative K algebra, and we showed that essentially every finite dimensional associative algebra is Morita equivalent to a bound quiver algebra, barring one statement. And I should first talk about that, and then we will move on to talking about goal 2, yeah, which is the main topic for today: radicals and irreducible morphisms. So yesterday I realized while I was writing this that the Gabriel quiver that I had defined here, associated with a basic finite dimensional algebra, I did not complete that. So let me quickly remind you what this Gabriel quiver is. Yeah, so here we are starting with a complete set of primitive idempotents as the vertex set, and then arrows from E to E prime are you take this. Yeah, basically you take the rad mod rad square, and then you take the dimension of this, or dimension, or to be more precise, we take a basis of these basis of this, and then we send it to, sorry, I mean that basis is how many arrows you draw from one place to another. Now the idea for constructing the ideal, yeah, because what we need is just quiver is not enough. We also need an admissible ideal apart from that. So how to obtain this admissible ideal? Yeah, so let me quickly show you how to do that. So an idempotent, so the quiver that we obtain uh, in this way is, so let A be an algebra, let A be a basic algebra, and I'm using the notation of Assem's book, Assem, Simpson, and Skoronsky, and let QA be the Gabriel quiver. So for Gabriel quiver, what do? We have some vertices, which I just mentioned, which are which form a complete set of primitive idempotents, and then we have some basis. So we actually choose and fix a basis. Yeah? We choose and fix a basis, and we send each base vertex. Yeah, vertex is a basis element here. So suppose A is an idempotent, then EA is the corresponding. So A is an idempotent in capital A, which means EA is the corresponding vertex, sorry, lazy path at the corresponding vertex. Right? If you have a lazy path at this vertex, then where should you send it to? Because if we want to define a morphism, an algebra morphism, then we should tell everybody where to send the generators. So this particular generator, the lazy path at an idempotent A, we send it to A itself. That is the only natural thing we can do. And secondly, if we have some morphism, then what do? Well, that morphism also we send it to, just hold on a moment. Morphism is in one-to-one correspondence with a basis, right? So X alpha is some element. So X, okay, so for any arrow alpha in QA, there exists a basis element X alpha, yeah, for this particular vector space, whatever I have written here, E dash, the radical modulo radical square, I mean, so okay. there exists a corresponding basis element, which I should ideally denote by J square A. Yeah, do you agree with this? That the ideal, we have this. Okay. So where should we send this particular element X alpha to? X alpha plus rad square alpha. We actually can make any choice. So we send this element to X alpha itself. So send it to X alpha. And then we have to show that whatever choice we made, it doesn't matter. Then we also can prove, yeah, it's a long proof, but you can show that there is a surjection defined this way. And then whatever is the kernel, so let me call this surjection pi, and whatever is kernel pi, then we show that this kernel pi is an admissible ideal. Okay, so that's our method of proving this result. Sorry, by a method of obtaining an admissible ideal. So that completes the description of the bound quiver. Any questions? Because this was a point, this was a missing point yesterday. Okay.
I have a question.
Yes, Tirtharaj, yes.
So, yeah, if you pick two primitive idempotents E and E prime in A,
Uh-huh.
and so you're considering this space E prime J mod J square E.
Yeah.
So the okay, so corresponding to one fixed basis element, the corresponding what will be the corresponding orientation of there? Is it from E prime to E or E to E prime?
Yesterday, I think we discussed that. So I have chosen the exact opposite convention of Schiffler because of the way I'm writing things. But if you choose and fix your orientation, then you will get opposite quiver or the original quiver. So you are not very far
Oh,
away
okay, okay.
from it.
Oh, I see.
Yeah.
Okay, okay, okay.
So in this case, actually, I mean, we are going to look at some dualities today. So it's not too much difference. Yeah, you'll simply get the opposite category, opposite quiver. All the properties, etc., will remain the same. Okay, thanks for the question. Right. So this was the point remaining from yesterday. Then there is another clarification which I should make. I think Sadanand asked this question. So I should correct certain things. So okay, let me quickly remind you that in order to fulfill goal 2, we started by defining what is an ideal in a module category. Ideal is locally a subspace, K subspace, which is closed under composition by arbitrary morphisms from either side. And then I made an erroneous comment here that an ideal I contains a split map if and only if I contains every morphism. So as I mentioned, this is erroneous. So this is not true. So in fact, what we wrote here, yeah, if suppose f from m to n is in I and f is a split mono, then there exists a G such that GF is equal to 1m. So therefore 1m belongs to I, and therefore every morphism from m to anything else, yeah. So therefore for all z, yeah, home mz will lie in this will lie inside I. And similarly, the other side. And for all y, home ym is also inside. No, sorry. Yeah, this is also correct. So these are the two things we can say, but we can't say anything more. Yeah, so not all morphisms, but all morphisms attached with that particular vertex, that particular module, they are inside. Any questions over here? Okay. So then our next job was to define the radical of the module category. And we followed our, like one of the equivalent criteria for defining the Jacobson radical of an algebra. We said that an element A belongs to the Jacobson radical if and only if for all elements B, 1 minus BA is a unit. Okay, so we use that particular criterion, and then we are saying that for all pairs of objects M and N, radical consists of those morphisms where 1 minus GF is an isomorphism for each G. Yeah, so we are using literally that definition. And we saw that if radical cannot contain any isomorphism, because 1 minus F inverse F is equal to 0, and 0 is never an isomorphism unless both the objects are 0 themselves. Yeah, in that case, 0 is equal to the identity of 0, and then it's yes, Irfan?
Yeah, so there for to define the radical of algebras. So we after the end of the day we saw that 1 minus AB or 1 minus BA didn't matter. So is that the
Yes.
same here?
Yes, it will be the same.
Okay.
Yeah, the direction won't matter. Eventually, yes, but right now we are just using one definition. I will also tell you another definition of the radical. Yeah, but I have to prove some result before that. Okay, so an isomorphism is not there, and it's a long proof, long but relatively straightforward proof to verify that radical is indeed an ideal, and that yes.
So a radical of semi-simple abelian category has to be 0. Is that immediate or?
Radical of a semi-simple abelian.
Semi-simple. Let's assume A is a semi-simple algebra and the module category is finitely generated semi-simple module.
Yes, then that will be trivial, yeah, because you can break that category down. Okay. I think in yesterday's tutorial, we did this. If you have a semi-simple algebra, then what will happen? You can break it down over an algebraically closed field. You can break it down as copies of K. And what will be K mod? K mod is just the category of vector spaces. So every morphism apart from that is invertible. And I think, no, wait, what am I saying? No, there will still be some non-zero morphisms in between vector spaces.
Okay.
But okay, let me think about it. So the third result here, it says that if you have something indecomposable, then only the non-split morphisms can lie in the radical between two indecomposables. And actually, the definition that I was anticipating is that it is the ideal of the category generated by irreducible morphisms between indecomposables. Or equivalently that non-split morphisms between indecomposables. So those are essentially the generators of the radical. So what are indecomposable morphisms in the case of K mod? They are simply I mean, just two copies of vector space themselves. Yeah. Right. So therefore, only zero morphism. Yeah. Only zero morphism is there. So I think, yes, your idea is correct that the radical would be the 0.
Okay.
Zero ideal, yes. Thanks for pointing that out, because I had not thought about it earlier. So for K mod, this will happen definitely. And therefore, for every semi-simple algebra, also the same thing will happen. Okay, so we are actually trying to prove the third property. And before that, we just noted that if you take the endomorphism algebra of a module, then its radical will be rad mm. Yeah, so we just noted that, which is sort of obvious. And we are proving the third property, that between indecomposable modules, we want to show that radical of Mn is same as those morphisms which are non-split. And yesterday we ended up by proving one side of this result. One side was this. So M and N are indecomposable. And what is the radical? Well, we want to show this equality, and an isomorphism, a split morphism between two indecomposables has to be an isomorphism. Yeah, and because of that property, we concluded that, and isomorphisms are not in the radical. We have already noticed that, so therefore this containment happens. Now let's do the proof of the other side. So what we are trying to show, like we have to start with a non-split morphism. So therefore it is, so let F be non-split. Okay. And let G be a morphism from N to M. Just some morphism be a morphism. Now, what can you say about GF? Then GF is a morphism in the endomorphism algebra of M. But now recall some result that we have already stated. The endomorphism algebra of an indecomposable. What can you say about that?
It's local ring.
Very good. Thank you. So it's a local algebra. So therefore, local algebra had one more characterization, that either every element is a unit or 1 minus that element is a unit. So we will try to see whether there is a contradiction. Yeah, so it is enough to show that GF is not an iso. Do you agree with this? We need to show that 1 minus GF is an isomorphism. So therefore, it is enough to show that GF is not an isomorphism. So suppose on the contrary that it is. Yeah, if GF is an isomorphism, well, then what happens? Then there exists some H such that HGF is equal to identity on M. Well, let me draw a simple picture for you to understand. Yeah, M is here, N is here, F is my morphism from M to N, G is my morphism from N to M, and H is some morphism over here. Now we simply have to do some algebraic manipulation. Okay, it's not difficult. So notice that. So now, what will be 1m square? It will be HGF square. Which I'm just going to highlight as this. So HG, FHG, F. Okay. And FHG square is what? FHG square is FHG, FHG. So this HGF is nothing but identity, and therefore you can conclude that it is FHG. what observations can you make out of this? That FHG square is equal to FHG, which means it is an idempotent. And where does it live? FHG lives inside the endomorphism algebra of object N. So therefore, FHG is an idempotent in endomorphism algebra of N. And which idempotents can exist? This is a finite dimensional module. So what idempotents can exist? Either 0 or 1. It's a local algebra. So only 0 and 1 are low idempotents over here. Can FHG be 0? I will wait for an answer.
Not really, right? Because 1m square is some product.
Exactly. Thank you. So FHG can't be 0 because 1m square has FHG as a factor. That's why I wrote it. Therefore, FHG is equal to identity on N. Well, this is a contradiction because this implies that F is split. F has one-sided inverse, F is split. This is a contradiction and that shows our claim. And that is how we conclude that the radical Mn between indecomposables is precisely the collection of non-split morphisms. And in fact, these are the generators. Okay, so if you take the smallest ideal generated by non-split morphisms between indecomposables, then it generates the whole ideal. Of course, what I'm saying needs a proof. One side would be clear, but those are the generators of the radical. Okay. Now,
so adding one small question. See, in radical, in some sense, measures the abstraction from being a semi-simplicity, assuming Artinian, at least in the finite dimensional algebra. A radical actually measures elements which are abstraction towards being semi-simple, right?
Okay.
So in this sense, in a module category, only everything decomposes into indecomposables, and between indecomposable being non-split is that abstraction of being not being split, or is that something like that? And these are the only precise abstraction towards being semi-simple.
Yes, I mean non-split morphisms.
In some sense, they are bad. They are not split. Is that?
I mean, I'm not sure. Like, if we call them bad, then we probably shouldn't be studying this subject.
Oh, okay.
Right? We are interested in studying these, and we are going to show that they still contain something manageable. Yeah, so split as you will see soon in next lecture or two, that split exact sequences, short exact sequences which are split, they are the best sequences. But what are the next best ones? Yeah, so they are like, here at least you can have a minimal bad thing. Yeah, in your language. Minimally bad is irreducible. Yeah, so those things where we will capture.
Adding more to that curious question, is there a notion of quotienting also?
Quotienting by what?
By this radical.
I mean, I haven't thought about it, but in general, yes, like if you have an ideal in a category which is two-sided, then you can quotient.
Okay.
Yes.
Thank you.
You can quotient. Yeah. Okay. So, right. So here the most important thing that you can do with radical is take its powers, because we want to see how factorable is a morphism. Yeah. So in fact, every morphism is only factorable up to a certain extent. Beyond that extent, it can't be factored. So I will say something about this now. So first of all, how to define powers of an ideal? Well, just like in algebra, you can define ideal square. Ideal square, if let me remind you something very quickly, maybe on this side. So what is ideal square? So normally if I is an ideal, two-sided ideal, let's say, of an algebra, then I square is summation, finite sums of elements of this I and j are elements in I. So finite sums of products of two elements. And we are going to say the same thing exactly over here. So what is rad to the power n? It is the k-span of n-fold compositions of maps in radical. No change here. We have to take the k-span, however. And if our algebra happens to be of finite representation type, then there will be some rad to the power L, which is 0. Do you agree with that? Some radical power would be 0. Because if we have seen everything, okay, maybe let us do an example. Yeah. So we have been looking at, in the tutorial, we have been looking at various configurations of ANs. So let us consider this as my orientation of AN. We all know what its indecomposables are. The indecomposable finite dimensional modules, if I arrange them using, if I write them using dimension vectors, then these three I'm writing as projectives. And there are arrows in this direction. Then there is something over here, which is 1, 1, 1. Then this is 1, 0, 0, and this is 0, 1, 0, 0, 1. This is the so-called Auslander-Reiten quiver of this particular configuration of A3. So these are irreducible maps. Either like there is one irreducible map between two indecomposables, or there is 0. That's all, up to scalars. So now if you look at this particular thing, and I'm going to highlight something using a different color. Now if I choose this as my M and choose this as my N, oops. Then can you tell me some morphism which lies in radical square? Any guess?
So this 0 from M to 111 with a module with the dimension vector 111. That is in the radical.
Module with the dimension vector 111.
Between that, there is a map that's in the radical.
Yes, all these maps which I have written, they are in radical.
So
yes, so what is in radical
such
square?
Very good. Map is
very good.
Radical
yes,
square.
Yes, correct. So this is what we compose. Yeah, we compose this map with this map. So basically what I'm saying, let me write it down in terms of representation so that everybody will understand, because many people don't attend tutorials. So this is 0, 0, and K. Okay, so this is our first representation, and this is your N. And then there is an obvious map between these. This is 1K, and this is 0, and this is 0. This particular projection map lies in radical square. Why? Because it can be written as composition of two maps, two irreducible maps. Okay. Any questions about this? That this lies in radical square. Okay. Now, what about, I'm going to use another color now. I will say this is my M and this is my N. What about them? Does there exist a map which lies in radical square? Between M1 and N1? If you go along any of those directions, yeah, then it will lie in radical square. And what about the zero map? Does zero map lie in radical square? Does it lie in radical cube? Does it lie? Is there any map here which lies in radical cube? Is there any map which lies in radical to the power 4?
I guess the radical cube would have to be 0.
Radical cube is, after radical cube, it is 0. Exactly. Yeah, because you have to talk about the chain. Yeah, definitely after radical cube, it is 0. But is radical cube non-zero or not? Yeah, I mean, this is something which you should probably think about. So there are some results which say that if you do not hit, so if you remember from the tutorials, we draw them in certain levels. So there are 3 levels over here. So if you do not hit another module at the same level, which is 2 steps apart, and you continue along these arrows, then the length of this path is precisely the radical, maximum power of the radical it lies in, the morphism lies in. That's a very interesting result that way. But however, here you still have to work out things because it goes like this and then again it goes back to the same level and it is exactly 2 steps apart and this. Okay, so basically I wanted to convince you that for finite representation type, means if the Auslander-Reiten quiver is finite, then some finite power of the radical is going to be 0. However, if it is not finite representation type, then we can't really say anything. Then we can have this so-called infinite radical. Infinite radical means the collection of all those morphisms which admit factorizations, I mean, which can be written as sums of compositions of at least n morphisms for any n. This is a bit mouthful. Yeah, what I'm saying, I hope you got the idea. Sums, so at least one of the summands of that map has n compositions for any n. So there exists a, like if you give me 1 million, then there is a factorization into 1 million. Some things. So this is how our radical to the power omega is defined. So finite representation type algebra has rad omega 0. And that is an if and only if condition. This is the result of Auslander. Okay, and we don't have to stop. Yeah, rad omega is not necessarily the stopping point. We can continue with rad omega plus 1, rad omega plus 2. We can continue through the ordinals. And for other ordinals, if you know a little bit about ordinals, then the property is that every ordinal can be written as a limit ordinal plus a successor plus finite number, finite ordinal. So every lambda can be written as gamma plus n, where gamma is a limit ordinal and n is a finite number. So the gamma that whenever we are talking about the limit ordinal, we simply have to take the intersection, just like we have taken here, the intersection until those ordinals. And when we are talking about some limit ordinal plus a finite number, we simply have to take the k-span of n plus 1 fold compositions. Yeah, this takes some time to understand. It's not exactly. So rad omega plus 1 is not rad omega dot rad 1. Yeah, rad omega plus 1 is rad omega times rad omega. Okay, so observe something here, that the category of the entire category contains the radical. Radical contains its square and so on. So this is a decreasing chain. However, we have started with the category of finite dimensional modules. So up to isomorphism, how many finite dimensional modules are there? Only a set. Many. Yeah, it's a set. And therefore, this chain, this decreasing chain cannot be strictly decreasing throughout, because ordinals form a proper class. Yeah, they are not a set. So you cannot be strictly decreasing. At some point, you are going to hit something which will stabilize. So rad infinity, the so-called stable radical, is the point where they stabilize. So this is the intersection of everything. We always know one morphism in rad infinity, namely the zero morphism. Zero morphism can be factored always as compositions of zeros of any order. And if you remember, I told you that the Auslander-Reiten quiver cannot capture everything. And I talked about the so-called transfinite compositions. And those transfinite compositions are what are captured by this rad omega. Rad omega is, it shows the morphisms which lie between modules in two different connected components of the Auslander-Reiten quiver. Okay, I think I have said a lot of theory. Let me do one example. So I'm going to start with the Kronecker quiver K2, which, if you remember, is this. I'm going to call them A and B. Yeah, this is our Kronecker quiver, and I have prepared one example for all of you. So let us consider this module. Can you, okay. The corresponding map at location A is 0, and the map here is identity. And the other map I'm interested in is the map, the other representation I'm interested in is the simple representation at vertex 1. Do you understand these representations? Yeah. If you have anything to say about this. And there exists a map between these two, namely identity and 0. This map commutes. Commutes with all these arrows, and therefore this is actually a morphism between two representations. Okay, nobody's saying anything, so I'm taking it as a yes that you understand that this works. Now I'm going to draw another morphism over here. This is k to the power n and k to the power n. And look at what happens over here. Now, obviously, you have to take my word for this, that all the diagonal entries are 0. Lower diagonal entries are 1. The super diagonal entries are, 1, and everything else is 0. And below, I just have an identity map. And okay, then first of all, observe that there is a morphism from here to here and here to here, of course, where I'm simply taking this 1, 0, 0, 0, 0. Yeah, it will be an n cross 1 vector of morphisms. So I'm simply including it as the first component. Can you quickly verify that this is a morphism? Okay, and n is arbitrary. Yeah, that is what I want to point out. So n is arbitrary, and I will draw another module over here, which is k to the power n plus 1, now in this case, and k to the power n. And let us write this down. So this is 0, 0, 0, and then 1, 1, 1 on the diagonals, and 0 here, 0 here. So it is n cross n plus 1 matrix, and at the bottom you have got the other way around. You have the identity matrix first, and then you have the zeros over here. Then once again, I want you to observe that there is a natural map from here to here. What does it do? It takes identity matrix. So 1, 1, 1, 0, 0, and then there is a row of zeros. And over here, it is just the identity matrix. And finally, there is a map which is simply, this is the zero map, and this is the first projection map. Okay. Yeah, perhaps how I came up with this would be a mystery, and I'm going to talk about it tomorrow. In tomorrow's tutorial, I will show you for a large class of algebras, finite dimensional algebras called string algebras, how to compute these Auslander-Reiten quivers and what these modules look like.
So you are saying the Jacobson radical for this K2 quiver is it's never going to be stable. Is that what
No.
saying?
Everything will be eventually stable. What I'm trying to show you, yeah, let me finish my statement.
Okay.
So I'm saying that the blue morphism between the original two can be factored as a composition of red morphisms. Okay. And these red morphisms, they work for every n. If you observe, then what I'm doing, k to the power n plus 1 and k to the power n. So the difference in these dimensions is exactly 1, which is also the pattern over here. So there is a chain, yeah, from n to n minus 1 to n minus 2 and so on up to 1, 0. So there is a chain of morphisms. All of them are irreducible. And at the top, what you have is dimension vectors are the same, 1, 1. Then 2, 2, then 3, 3. So basically, there is an infinite descending chain at the top and infinite ascending chain like at the bottom. And the composition of this transfinite series of morphisms is the blue morphism. So this particular morphism, the blue morphism that I have written, it actually lies inside the infinite radical. That's the point of this illustration.
Okay.
So just to confirm, technically to make this work, you need to actually construct the maps for every m and n, not just 1 and n, right?
For every?
To make this work, you have to define a map for
yes,
m less than or equal to n and not just 1 and n, right?
Yes, that's correct.
And we also have to show that they're all irreducible.
They are all irreducible, correct, yes. So there is a chain, an omega chain, followed by an omega star chain of morphisms, and they together give you this composition. Yes, I think somebody else also started talking. Are there any other questions? Okay. So I wanted to give you an example of a morphism which lies in the infinite radical. And in fact, in this case, as it turns out, omega plus 1 is the stable rank. Yeah, stable rank is the least ordinal where this chain stabilizes. Okay, and what is this? Well, okay, I should also give you one more definition, yeah, which is quite obvious now. So you take any morphism F, yeah, what is the rank of F? So rank of F is the least ordinal alpha such that F belongs to the alphath power, but it doesn't belong to alpha plus first power. Yeah, if this is defined or infinity otherwise. I mean, if such a minimum doesn't exist. Because, for example, consider 0. 0 will belong to all ordinal index powers of RAD. So we have a well-defined, but this arithmetic of ranks is quite weird. And you have to work a bit. So every morphism has a rank. Yeah, so that's a nice thing. And I believe like such things can be used elsewhere if you have some notion similar to an irreducible morphism. I don't know any other scenario in which this can be used. And I will show you how the arithmetic of radical works through this particular proof now. Okay. So we are going to look at the proof of this theorem that a map is irreducible if and only if it belongs to RAD but not RAD square. So recall, an irreducible map is one where you have it's non-split first of all, and whenever you factor, then either the first one is split mono or the other one is split epi. Okay, so that's our characterization. So let's try to prove this. So since F is irreducible, it is non-split, and therefore it belongs to radical. Yeah, because oh sorry, I mean I think I'm forgot to say something over here. I should add that in the hypothesis, otherwise this won't work. M and N are indecomposable. Yeah, and we are using the result that we proved earlier to conclude this. M and N are indecomposable, and since F is irreducible, non-split, therefore it belongs to radical. If F factors through some object, well, what would that third object look like? Because it is in category A mod and we have Krull-Schmidt property, it must look like a finite direct sum of indecomposable. So all these xi's are indecomposable. Now, because it is irreducible, what do we know? Either this G is a split mono or H is a split epi. Okay. So what will happen now in this case? Suppose G dash satisfies this G dash G is equal to identity M. Well, now this is a matrix equation, so matrix identity. So we write G dash as a row vector and we compute this, whatever this is, summation Gi dash Gi. Then first of all, notice that Gi is in radical. Can you tell me why Gi is in radical? Oh, maybe I think I haven't mentioned one thing. So we are assuming that hold on. Okay. So basically, what I'm assuming, we are trying to prove a contradiction to the assumption that f is in rad square. When would f be in rad square? If it can be factored as this, as hg, where both h and g are in radical. Okay, so I'm assuming that G is in the radical, and therefore each Gi is in radical because it's simply composition of G with appropriate projection map. So if each Gi is in radical, then this sum will also be in the radical because radical locally is an abelian subgroup. So Gi dash Gi is in radical because it's closed under composition, and then sum is also there, which means the identity is there, which is a contradiction. Yeah, no isomorphism can belong to this. So therefore, our assumption that G is a split mono leads to a contradiction. Similarly, if we assume that H is a split epi, then we will get a contradiction. And these two contradictions show that F is not in rad square. Any confusion?
Can we not
Yes.
directly say that if G is split, then it cannot be in the radical? Because you cannot have a split map in a proper ideal.
But we want to show that it is not f is not in rad square. How will you do that?
I mean, so your just starting assumption was that you factored f as hg with both h and g in the radical, right?
Yeah, if you assume that.
So then that would automatically force both h and g to not be split.
Okay. Okay. I think, yeah, we should just directly start with G is a split mono, and then that leads to a contradiction. H is a split epi, that leads to a contradiction. We shouldn't have assumed that H and G are in, no, but for this particular thing, we need that Gi is in radical. We don't have that if we don't assume what I said. Yeah, Raghuram, you wanted to say something? I'm not sure whether he's here. Might got this. Yeah. Yeah, Raghuram, you wanted to say something?
I mean, if G is in the radical, then 1 minus G prime G would be invertible, right?
Yes. So we are not saying that either. Okay, yeah, you are trying to give a direct proof. Yeah, I can see that. Yes. Thanks. Okay, so let's do the other side. That if f is in rad but not in rad square, then again f factors as above. If no Gi or Hi is split, then f would be in rad square. We are just using the same diagram again. So f would be a sum, finite sum of compositions of two maps in the radical. None of them are split. And Gi and Hi being split is enough. Non-split is enough, right? Because each xi is indecomposable. M is indecomposable, N is indecomposable. So this will lead to a contradiction, which means some Gi has to be split or some Hi has to be split, which means either G is a split mono or H is a split epi. So this actually allows us to define the Auslander-Reiten quiver technically. So the number of arrows from the isomorphism class of M to isomorphism class of N, where M and N are both indecomposable, is the dimension of rad modulo rad square between M and N. Yeah, so this result is the key to defining that, because earlier, if you remember, I had just said that take the maximum number of linearly independent irreducible morphisms. But here now I'm actually defining it as dimension of certain vector space. Put those many arrows over there. And you should also observe that this expression is similar to the expression for Gabriel quiver. How many arrows to put in the Gabriel quiver? Okay. Any questions so far? So far we have completed the discussion of goal 2. Okay, so I'm going to stop sharing this particular file now, and I will share something else. So thanks to Sadanand, I've downloaded a new app where writing is easier. It is this app. Journal, perhaps. That's the name. Okay, so we are going to talk about a bit of homological algebra over here now. And I'm trying to do this because I want to help people who do not have enough background in homological algebra. If you have any questions, please stop me, because just at least a primary understanding of these concepts will give you a better idea of connecting the dots in the larger picture of Auslander-Reiten theory. Here I'm trying to follow this human way of looking at pictures. Yeah, I like to, when you are shown a painting, then you try to identify the elements of a painting. Yeah, you don't work like a computer. A computer will analyze a painting pixel by pixel. We don't do that. We have to first analyze the bigger components, and then we have to see how they interact with each other. Yeah, so the purpose of my part of the course is just to give you that bigger picture and how different components move. If you become interested, which I seriously hope, then you will automatically fill in the details. Okay, so let us start with the finite dimensional algebra A, and home is a bifunctor in this case. Yeah, home, you have to take two modules, home Mn. Home Mn is contravariant in the first component and covariant in the second component. Contravariant covariant means covariant means it doesn't change the direction of the arrows. Contravariant means it reverses the direction of the arrows. Yeah, which you can equally write as by writing an op at the top. And the important thing to observe here, yeah, in general, if you are talking about a non-commutative ring, then the target of the home bifunctor is just the category of abelian groups. Yeah, if you have only seen commutative algebra, then you would know that it again goes to A mod, but that is not necessarily the case. Yeah, it's only abelian groups. Okay. So hopefully you know what an exact sequence is, a short exact sequence and a long exact sequence. So exact sequence means at every term, every intermediate term, the kernel of the next map, the map leaving that is equal to the image of the previous map. Okay, that's our main definition of this. So therefore, the composition is 0 and something more is true. Right, so given a short exact sequence like this, 0, x, y, z, 0, in the category of modules, and given a module M, we can obtain two exact sequences in general. Yeah, so you can just apply home at every point, and you will get a 0 in the beginning, then home mx, home my, home mz, but you don't necessarily get the last 0. So this is called the left exactness of the covariant home functor. The last 0 doesn't appear. I mean, the reasons are will be clear soon. because 0xyz0 is an arbitrary short exact sequence. We need to have some property on M so that this the home functor takes all exact sequences to all to exact sequences. And dually, because we have contravariance in the first component of the home functor, we get 0 home Zm home Ym home Xm, but again we do not get the last 0. Now, if you are interested in knowing what exactly is happening at this point, then perhaps I will write this. So if this is F, then what you are doing here is, if you have a morphism from M to X, you are simply taking F composed with blank, and over here you are taking blank composed with F. If this is your first time looking at these things. So again, this is also called the left exactness. The 0 on the left is preserved, which means kernels are preserved, co-kernels are not. Yeah, even though the direction of the sequence had changed. Yeah, Z first, Y, then Y, and then X. Okay. So we say that a module is projective if home P blank is exact, which means it takes exact sequences to exact sequences. Now, because of left exactness, the only thing that is lacking is whether it takes this last epimorphism from Y to Z to a surjection. Yeah, so given a G over here, where is that? Okay, given a G over here, is G composed with blank surjective or not? So which means it has to map epimorphisms to surjections in abelian groups. Or equivalently, you can show that every morphism with target P, every epimorphism with target P will split. Yeah, so which means there exists a map in the opposite direction from P to Q such that if you complete the cycle and come back to P, then you've got identity. Or equivalently, because we are working in modules, we also know that this is a direct summand of a free module. So these are all equivalent criteria for projective modules. This is similar to commutative algebra. Yes, Riju?
Sir, like earlier you said kernels are preserved but co-kernels are not. Could you please elaborate on what you meant by that?
Okay, so if you look at the morphism G in this exact sequence, then what is the kernel of G? It is the monomorphism F. I'm using like a category theoretic terminology, or an object X, you can say object X together with the morphism F. That is the kernel of G. So that is preserved. Yeah, kernel is preserved means what is kernel of G? It is F. And what is kernel of G composed with blank? It is F composed with blank. That is what I meant by that. But co-kernel is not preserved. G is the co-kernel of F, but that is not necessarily preserved. Your object P has to be projective for that. Okay. So equivalently, it can be a direct summand of a free module. Yeah, this is the normal thing that people usually know. Projective means direct summand of a free module. Dually, we can define injectives, but here we are talking about the contravariant home functor. So home blank I is exact, or it takes monos to surjections, or every mono with source I splits. We don't have a fourth condition in general, okay? The fourth one is special to only projective modules. It's not a direct summand of a free module. Okay. Injectives are quite weird in general. Yeah, projectives are much simpler to understand. However, in the case of finite dimensional algebras, that won't be the case, as I will show you. So we just give some names. A-proj and A-inch are the full subcategories consisting of projectives and injectives. We'll need these categories. And they are both closed under direct sums as well as direct summands. Finite direct sums, finite direct summands. Okay. These are some interesting properties. And one general observation, which we will revisit in due course of time, is that given any morphism M, given any module M, there exists a projection from a projective. Okay, there exists a projection from a projective. So that is why it is called a projective. This actually shows like the choice of word. Now, the simple idea would be you take the free module generated by the elements of M, and then you quotient. Then you take the natural quotient where you just define the map on generators as the element goes to itself. A generator named A will go to the element A in M. Yeah, but you can also find out something better. Yeah, but I just wanted to talk about the existence, and dually, every module can be embedded inside an injective module. I mean, in the category of abelian groups, you can do this by using rational numbers. So the abelian group of rational numbers that is injective, so you can embed anything into some direct product of copies of rationals. But in general, like the proof is harder than the corresponding projective version. Okay, so let us look at something more. So we want to talk about homological dimensions of different objects. So give just because of this pink statement or magenta statement that every module can be covered by a projective, we can iterate this process. So let us start with a module M. Then we take some projective P0 which maps onto it, and then you take the kernel. Whatever that kernel is, you can take some projective module P1 which maps onto it and again take its kernel, and so on and so forth. You continue this process. This map F1 is the composition of this P1 to kernel epsilon followed by the embedding inside P0, and so on and so forth. So this way you can obtain a possibly infinite sequence of projectives and morphisms between them. Okay, so this one, and I have already drawn what are the short exact sequences in this. I have highlighted them using different colors. So the projective resolution of M is just this P0, P1, P2, and dot, dot, dot. I mean, I'm using the correct technical term here. In a projective resolution, M doesn't appear. You have to chop it down, truncate that sequence at P0 and just put a 0 afterwards. And this sequence is not exact. This is a sequence entirely contained of projective modules. That's why projective resolution. It is not exact at P0. Everywhere else it is exact. And how can you recover M? Well, by taking P0 divided by image of F1. Because it's simply the co-kernel of that. Okay, so if you know the language of homology, then this is the zeroth homology of this projective resolution. You can recover that object. So basically, my idea is that you don't really lose a lot of information even if you are doing this. You don't lose the object. However, there is a cost to pay. Instead of dealing with one object, now we are dealing with a chain complex of projectives. So we are talking about a much larger object, and dually, you can define an injective resolution that you are taking up. You do the exact reverse process. You reverse all the arrows in this and use that the category of modules has enough injectives, and therefore you keep on doing that, which means embeds inside an injective module, and you keep playing the same game, and you can recover M in this case as kernel of the first map. Okay. However, the cost that we are paying here is something more actually, that these resolutions are not necessarily unique. If you know something called like something more some more advanced concept in homological algebra, namely chain homotopy, then it is unique up to chain homotopy, but actually it is not unique. Not unique up to isomorphism at least. However, in the case of finite dimensional algebra, that will be rectified. Yeah, we will have a unique way of constructing a projective resolution that will be called minimal projective resolution. Okay. But before we go there and talk about this spatial case, let us establish some more things. So projective dimension of a module, which we write as PDIM of M, is the least D such that M has a projective resolution with D plus first term 0. Okay, so it may or may not become 0. If it becomes 0, then you count that last non-zero D. Otherwise, you say it is infinity. And dually, you can define injective dimension. Okay, so notice that if M is projective, yeah, if M itself is projective, then what could be chosen as P0? Just M. And then the kernel of that map, kernel of the identity map is 0. So therefore, the projective resolution will be truncated. So therefore, the projective resolution, projective dimension of a projective module is 0, and the converse is also true. Okay. Similarly, a module is injective if and only if its injective dimension is 0. Well, what can we do with this? We can compute the global dimension of the algebra itself using these projective dimensions of its modules. So the global dimension of algebra is defined to be the supremum of the projective dimensions of its modules, finitely presented modules. Yeah, this may be finite, it may be infinite. Yeah. So we'll see some examples. So today's tutorial, we will look at some examples and we'll compute some global dimensions. Okay. And you can, I mean, there is some work to do, but whether you use projective dimension or injective dimension in the definition of global dimension, it doesn't matter. It's still invariant. Okay. So say that an algebra A is hereditary. This is maybe looks like a detour. If every submodule of a projective module is projective. Okay. So basically, what will happen in this case, if every submodule of a projective module is projective, you look at again this sequence. So I started with some M, then I got some P naught, then kernel of epsilon is a submodule of P naught. And because it is a submodule, kernel of epsilon itself will be a projective module, which means I don't have to go any further. I can like P1 is kernel epsilon and then I'm done. After that, there is nothing. So which means if this happens, then the projective dimension of M is always going to be 1 or 0. Okay, which means the global dimension is at most 1. Okay, so now this is the result that I have written. So global dimension of an algebra is at most 1 if and only if the algebra is hereditary. Even the converse can be shown because converse precisely says the reverse thing. That submodule of a projective is projective. Yes.
Sir, I have one doubt. Sir, we said that the module itself is projective. So its dimension should like
No.
would it
I'm
not
saying
be
that
0?
submodule of a projective module is projective. But I may start with a non-projective module. Then I try to construct its projective resolution. It will only have P0 and P1. And P2 will always be 0. Yeah, I mean, P2 can always be chosen to be 0. That's my claim.
Thank you, sir.
Okay. And the path algebras for quivers, yeah, they are actually hereditary. Yeah, this is a relatively straightforward proof. You just have to follow your nose and you will reach there. I'm not going to do this proof, but you can verify by using.
Is it even true if Q has oriented cycle?
Okay, let me think. No, I have assumed that A is finite dimensional at the beginning itself. But I believe that it is true even otherwise. Because we are just talking about homology, dimensions don't play any role here.
I see.
Yeah. And maybe there was some other question. Okay. Fine. So, okay, now I think I can rephrase some.
What is this analog in the sense of injective modules?
What is the analog in the sense of injective modules?
The definition of hereditary.
I mean, I have never heard of that. Every quotient of an injective is injective, yeah, which is. See, injective modules in general are not very friendly. However, in this case, in this very special case, injectives and projectives are not very different. Yeah, I will come to that soon. Because they were defined in similar way, right? Projective modules were just left ideas and injective modules were right ideas generated by the same primitive element. So there should be a perfect one-to-one correspondence between them. And we will show that soon. Okay, so now let me try to rephrase one result that Upendra proved. Upendra proved Gabriel's theorem last week. And Gabriel's theorem only talks about path algebras for acyclic quivers. So the trichotomy that I alluded to in the first lecture of mine, the trichotomy, Drost and Crowley-Bouvier trichotomy, that every finite dimensional algebra is either finite representation type, tame representation type, or wild representation type. So he actually proved the result for all hereditary finite dimensional algebras. So Gabriel's theorem, like if you want to look at it from an algebraic perspective and not look at quivers, then for all hereditary algebras, he proved this trichotomy in terms of quadratic forms. Okay, so just wanted to point that out. Any questions at this point? Okay, so let's go ahead. And we are now going to talk about some dualities. And we'll compose two dualities. I mean, some functors, let's say, and it will restrict to a duality. Yeah, it's a very nice piece of algebra/category theory. So we are planning to construct a functor called the Nakayama functor from the category of modules to itself. So it's a covariant functor. But we'll be writing it as a composition of two contravariant functors. Yeah, and as we teach school children, that two negatives means one positive. So two contrapositive functors means one covariant. Two contravariant functors will give us one covariant functor. Okay, so this is defined as the composition of these two things, B and home blank A. Okay, before you look at anything that is written on the screen, just think about basic category theory. Yeah, if you are given a finite dimensional vector space, then the dual of that, namely home VK, we are taking all the functionals on that vector space. The dual is also finite dimensional, right? And if you take the double dual in that case, then you will return where you started up to isomorphism. So which means it is a perfect duality. Taking the dual is a perfect duality. So D goes from vector spaces to vector spaces. So K mod to K mod, and it doesn't change anything. However, it is a contravariant functor because it is home blank K. Okay, it is home blank K, so it is contravariant. So that's why it's not called an equivalence. Yeah, equivalence is when you have one category to another category and the covariant functor where everything nice happens. Whereas if you have C op and D and there is an equivalence between them, then we call it a duality. That's the definition of duality, equivalence between the opposite categories. So the category of vector spaces, finite dimensional vector spaces, is equivalent to its own opposite category. Okay, enough of category theory. However, this other thing which we are talking about, home blank A, yeah, that is not so nice. Yeah, it's not a perfect duality in general. Yeah, we'll have to talk about it a little more. So home blank A will obviously go from, it's a contravariant functor, so it will go from A op mod, sorry, A mod op to mod A. Or equivalently from A mod to mod A op. I mean, you just have to put op on one side. Well, let me show you what it does. It takes a morphism from M to N and it maps it to precomposition with G. Okay, now here I need to highlight something. So if you look at these two A's, yeah, here I'm using the concept of a bimodule and look at the highlighted A's. They are consumed. So the left module structure is consumed by the home. So therefore, the final result, as I pointed out, it's just an abelian group. However, in this very special case, because we are talking about the algebra itself, algebra has got a left module structure as well as a right module structure, which means it is a bimodule. A is an AA bimodule. So this right module structure, this double underlined bimodule structure is what gives that home blank A right module structure. If I had replaced home blank A by home blank X for any other X, then that wouldn't necessarily be true. So I'm utilizing the bimodule structure and it becomes a right module. And the direction of the arrow is reversed. Yes, Irfan?
Sorry. Yeah. So, but if we, for example, replace home dash A by home dash X for some left A module X, then after applying home A, rather after applying home dash X, then you will get a right A of action, right?
No, you won't get any action. Actually, if you just have a left module structure on X, then you don't get any action.
No,
You have
I'm
consumed
trying to
it.
use the property like if X is a left A module, then you can make X as a right A op module.
No, that is true. But whatever that right A op module structure it is consumed by the home itself. Yeah, this is a speciality of non-commutative rings.
Oh, I see.
Yeah, therefore we are only talking, and just because this happens to be a right module, A happens to be a bimodule, we get that we land inside mod A. However, the direction of the arrows is reversed. Okay, that's all I wanted to point out. And then finally, what is happening? I mean, this is the duality which is home K blank K, which is from mod A up to A mod. Yeah, what we are doing is take a map from YA to XA in mod A, right modules. Then in the opposite category, we have a map going from XA to YA. And then it is blank composed with H in A mod. So you can verify all these details. What I just wanted to show you is that by composing these two functors, we do get a covariant functor. So D home blank A. Yeah, so that's our Nakayama functor. Okay. Now, suppose, yeah, A is KQ mod I or just KQ. Just think about the path algebra. The proofs will go through even if it is a bound quiver algebra. Then what is a projective module? Projective module, I'm just going to write as projective module over Q. Yeah. So projective module PI, if you remember, it is what is its basis at J? Like PI sub J is has basis of all paths from I to J, which are not killed by the relations, but let's assume we are working with the path algebra. So all paths from I to J. Okay. Now you should also remember one thing, that we wrote the identity in the path algebra as a sum of all primitive idempotents, as the sum of all lazy paths. One is equal to summation EI. And as a consequence also, we wrote that the left module A, the left regular module A, is a direct sum of all the projectives. Hopefully you are with me. So what I'm talking about is this first line. Yeah. Home PI, yes.
Yeah, just to consolidate. So can you just go a step above?
Okay.
So the Nakayama functor takes a module M and maps it to form A M comma A dual.
Yes, home M comma A comma K. Yeah.
Oh.
Yeah. Right. So PQI, I have written in the first component. I want to apply this Nakayama functor on a projective module. Okay. So I'm taking home PQI comma A, which is isomorphic to this, because what is A? A is nothing but direct sum of PQJ, where J varies in Q0. Yeah, we have this standard decomposition of the left regular module in terms of projectives. This also coincides with our definition of projective, that these are direct summands of free modules. So this is the free module. Okay. And because the home functor is left exact in both components, you can take that direct sum out. So PQI, PQJ. Now again, recall what Upendra said. Yeah, that we are using some kind of Yoneda lemma over here. So therefore, home PQI comma PQJ, what is that? You simply evaluate this PQJ at I. I mean the ith position of PQJ. You are just taking the direct sum of those. This is Yoneda. Nothing more. Okay, but try to read that. Yeah. What is the basis of PQJI? The basis consists of all the paths from J to I in Q, which means all the paths from I to J in Q op. If I just reverse the direction, and therefore my last line, that it is simply the projective module at vertex I for the corresponding dual, for the dual quiver. Any questions so far?
Why does the last isomorphism hold as A modules?
Because I mean, yeah, you just verify that the module action works. It's trivial. Okay. Okay, so the last line I plan to say today, now you do the duality. Duality D, you apply that. So you will actually get back the injective module at I. Now, this is something you need to verify. I'm not going to show that. You need to convince yourself that the Nakayama functor applied at a projective module gives you the corresponding injective module. Okay. And well, okay, let me finish this line as well. That D is a duality on all modules because all of them are finite dimensional, nothing really changes. You just get back your D square is identity or isomorphic to identity. And the restriction of the first functor that we took, A proj to proj A op, is a duality. So restriction, co-restriction of the first one is a duality. Because I just told you that PQI goes to PQ op I, but you can come back. PQ op I will go to PQ op I. But what is Q op? The double dual is just Q. So when restricted to this, it is again a perfect duality. And therefore, the restriction from projective modules to injective modules is an equivalence of categories. And because it's an equivalence of categories, and if you believe that projective modules PIs are indecomposable, then the corresponding IIs are also indecomposable. Because whatever happens has to happen on both sides simultaneously. Projectives and injectives are closed under direct summands and direct sums. And any equivalence will also preserve direct sums. Okay, so
this is not an equivalence at the general level. Right?
No, it's not an equivalence at the general level. But we don't need an equivalence at the general level either. Yeah, that's the beauty of this theory. We will only need it. So we'll take a module, we'll replace it with a projective resolution. We'll use some part of that projective resolution, we'll apply the Nakayama functor, and then through that we will define the corresponding Auslander-Reiten translate. Yeah, that's our job for tomorrow.
Okay, but isn't that duality means a contravariant equivalence?
No, but I'm saying this is not a duality. This is a perfect equivalence of categories. Did I say duality orally?
So this is not, I mean, can you go slightly up?
Yeah, sure. Here. I'm just saying Nakayama functor. Yeah, I'm not saying duality. Composition of two dualities is an equivalence, but there is a perfect bijection between these two, projectives and injectives.
Okay.
That's what we need. Okay. Any questions?
Yeah, just a comment. So can you please go to that?
Which one?
Yeah, maps for hom-A.
Sure.
So yeah, so yeah, here it is. So here you are taking this hom-MA on the right hand side, first line after the map is defined. So there, okay, I understand this hom-MA only has this group structure, maybe more, maybe vector space structure, because M and A both have. So since this A is also a right A module, that actually makes this hom-MA right A module, isn't it?
Yes.
Okay.
So you take any homomorphism, and then after you have applied that homomorphism, then you multiply by the scalar from A on the right. And that's the action.
Yeah. I mean, so instead, instead of A, if you take any left module X, let's say, so then this hom-MX, so you can take. So doesn't that belong to mod? I mean, right mod A op?
please try to verify that. See, there is one condition where, let's say, R and S are scalars. So RS acting on M is equal to R acting on SM. This is the differentiating property between left and right modules. Yeah, so try to verify that. So what I like to say in a short is that the left module structure is consumed by the home. Yeah, you will never get it back.
I see. Thank you.
Maybe also Irfan, both if I to define a harm, we need both slots to be a left A modules, right?
Yes.
Yeah, I mean, yeah, I mean, what I had in mind, like to consider X as a bimodule where the action of A from the left and action of A off from the right, something like that. What I had in mind, but I don't know.
That's you are just making a tautological statement. You are just using the same module structure twice, which doesn't really help.
That is true. Yeah.
Okay. Okay, I will stop recording and I'm still here if you have any